Find the minimum cost of tomatoes. In this problem, there is a demand for whole tomatoes, tomato juice, and tomato paste of 4,000 pounds, 3,000 pounds, and 6,000 pounds, respectively. These three tomato products shall be produced using a combination of grade A tomatoes, which cost 10 cents per pound, and grade B tomatoes, which cost 5 cents per pound. Associated with each grade of tomato is a quality rating. Grade A tomatoes have a quality rating of 9, and grade B tomatoes have a quality rating of 5. Furthermore, each product has a minimum quality requirement. The minimum quality for whole tomatoes, tomato juice, and tomato paste is 8, 6, and 5, respectively. So far in this problem, we can identify 6 decision variables. That is, there are 2 different grades of tomatoes that can be used for 3 separate tomato products. Decision variable XAW will refer to the quantity of grade A tomatoes in pounds purchased to produce whole tomatoes. Decision variables XAJ and XAP will refer to the quantity of grade A tomatoes in pounds purchased to produce tomato juice and tomato paste. Likewise, decision variables XBW, XBJ, and XBP will refer to the quantity of grade B tomatoes in pounds purchased to produce these 3 products. Using these 6 decision variables, we can formulate the demand and quality constraints. The total demand for whole tomatoes is 4,000 pounds. Therefore, the quantity of grade A tomatoes needed to produce whole tomatoes plus the quantity of grade B tomatoes needed to produce whole tomatoes must be at least 4,000 pounds. The total demand for tomato juice is 3,000 pounds. Therefore, XAJ plus XBJ must be at least 3,000 pounds. Lastly, the quantity of grade A and grade B tomatoes purchased for tomato paste must be at least 6,000 pounds. The minimum quality rating required for whole tomatoes is 8. Therefore, the weighted average of the quality rating of grade A and grade B tomatoes used to produce the whole tomatoes must be at least 8, where coefficients 9 and 5 refer to the quality rating of grade A tomatoes and grade B tomatoes, respectively. The minimum quality rating required for tomato juice is 6. Therefore, the weighted average of quality rating must be at least 6. And the minimum quality rating required for tomato paste is 5. In this problem, there are 3 demand constraints and 3 quality constraints. However, after simplified, the quality constraint for paste is always satisfied and can be removed from the constraint set. To put the constraints into standard form, we'll add slack variables dw, dj, and dp to the left-hand side of the demand constraints to account for the unmet demand. Since unmet demand is not acceptable, we'll assign a large cost to these 3 variables such that all demand will be met. Variables qw, and Qj will be subtracted from the left-hand side of the quality constraints. These surplus variables allow for the quality of each product to be greater than the minimum. Lastly, all variables in this problem shall be non-negative. Setting up the network tableau, only a portion of which is shown on this screen, the cost for grade A tomatoes is shown to be 10 cents per pound, and the cost of grade B tomatoes is 5 cents per pound. Initially, the slack and surplus variables are basic and equal to the right-hand side. All 6 X decision variables will begin non-basic and equal to 0. The initial costs associated with the Q variables is 0, since there is no penalty if the quality of the product is higher than the minimum. However, the decision variables dW, dJ, and dP are assigned the high cost of 1 as a penalty so that the supply is at least the demand. To begin the simplex method, a pivot operation is performed on all 5 basic variables: QW, QJ, DW, DJ, and DP. After the pivot operation, the reduced cost coefficients for all non-basic variables are negative. In this first step, we'll select variable XBP, which refers to the quantity of grade B tomatoes used in the paste, to enter the basis in place of variable DP, which refers to the quantity of unmet demand for tomato paste. The pivot operation involves adding 0.95 times row XBP to row Z. Next, we'll choose variable XAJ to enter the basis, because it has a negative reduced cost coefficient. As an aside, if we chose XBW or XBJ to enter the basis, their values would equal 0 from the ratio test, and there would be no improvement in the value of the objective function. Therefore, we'll pivot about variable XAJ by adding 0.90 times row XAJ to row Z, and adding 3 times row XAJ to row QJ. Next up, variable XAW, which refers to the quantity of grade A tomatoes to be used for whole tomatoes, will take the place of variable DW, which refers to the quantity of unmet demand for whole tomatoes. After pivoting about variable XAW, the tableau is updated. Next, variable XBW will replace QW. Pivoting about XBW involves first dividing row XBW by 4, then adding 0.05 times row XBW to row Z, and subtracting 1 times row XBW from row XAW. Lastly, variable XBJ, which represents the quantity of grade B tomatoes to be used in tomato juice, enters the basis for variable QJ, which refers to excess quality in tomato juice. After pivoting about XBJ, all non-basic cost coefficients are positive, which confirms we have reached a unique optimal solution. The values of these optimal decision variables are shown on the right-hand side of the tableau in column B. For this problem, The optimal solution is to purchase 3,750 pounds of grade A tomatoes, 3,000 pounds to be used for whole tomatoes, 750 pounds to be used for tomato juice, and 0 pounds for tomato paste. We also need to purchase 9,250 pounds of grade B tomatoes, 1,000 pounds to be used for whole tomatoes, 2,250 pounds to be used for tomato juice, and 6,000 pounds to be used for tomato paste. These 6 values make up the optimal X vector, X star. The cost vector equals 10 cents per pound for grade A tomatoes and 5 cents per pound for grade B tomatoes. The minimum cost is C transpose X star, which equals $838. When reviewing the possible solutions, the answer is B.